Hello everyone and welcome to Coders of Pune. Today we're diving into Unit 3 of Computational Statistics, a crucial subject for AIML honors students. In this video we'll break down the essentials of hypothesis testing, p-values, t-tests, ANOVA and more. Whether you're new to these concepts or looking to strengthen your understanding, you're in the right place. We'll start with the basics and gradually build up to more advanced topics, ensuring you have a solid grasp of each concept. So let's get started and unlock the power of statistical thinking together. Unit 3 focuses on hypothesis tests and statistical tests. We'll explore the analysis procedures used in real-world data scenarios, ensuring you can extract meaningful insights and patterns. These skills are foundational for building models that help achieve your objectives in data science and machine learning. By the end of this unit, you'll be comfortable with the step-by-step process of hypothesis testing and understand how to apply these methods to real datasets. Real-world scenarios, data analysis follows 6 key procedures. These steps help us extract insightful meanings and patterns from data, ensuring our models are both accurate and reliable. From data collection to interpretation, each procedure builds on the previous one, creating a structured approach to solving complex problems. Mastering these steps is essential for anyone looking to make data-driven decisions or build predictive models in the field of AI and machine learning. Start with the basics. A hypothesis is a claim or assumption about a population parameter. Hypothesis testing is a statistical procedure that evaluates the assumption using sample data. For example, a company might claim its new drug has no effect on blood pressure. Through hypothesis testing, we use a structured process to determine if there's enough evidence to support or refute such claims. This process is fundamental in scientific research and data analysis. Hypothesis testing, we deal with 2 competing statements. The null hypothesis H0 is the default assumption. Think of it as the status quo. For example, the company's claim that the new drug has no effect is the null hypothesis. The alternative hypothesis H1 or HA is the new idea or theory we want to test, such as believing the new drug actually lowers blood pressure. These 2 statements are always in direct opposition, and our analysis aims to determine which is more likely given the data. When we conduct a hypothesis test, there are 2 possible outcomes. First, we might reject the null hypothesis, which means there's enough statistical evidence to suggest the null is likely false. This outcome indicates that the observed results are not due to random chance. Alternatively, we may fail to reject the null hypothesis, meaning the data doesn't provide a strong enough case against it. Importantly, failing to reject doesn't prove the null is true, it just means we don't have enough evidence to say otherwise. Errors can occur in hypothesis testing when our decision doesn't match reality. There are 2 main types, type I and type II errors. A type I error, also known as a false positive, happens when we reject the null hypothesis even though it's actually true. The probability of this error is called alpha. On the other hand, a type II error or false negative occurs when we fail to reject the null hypothesis even though it's false. The probability of this error is beta. Understanding these errors is crucial for interpreting test results. Type I error or false positive occurs when we incorrectly reject the null hypothesis even though it's actually true. Imagine a doctor diagnosing a healthy patient with a disease. This is a classic example of a type I error. The probability of making this mistake is represented by alpha, which is set before the test begins. Keeping alpha low helps reduce the risk of false positives, ensuring our conclusions are more reliable. Type II error or false negative happens when we fail to reject the null hypothesis even though it's actually false. For instance, if a doctor tells a sick patient they are healthy, that's a type II error. The probability of this error is beta. Balancing the risks of type I and type II errors is a key part of designing effective hypothesis tests, as both can have significant consequences depending on the context. Confidence level is a measure of how sure we are that an interval estimate, like a confidence interval, contains the true population parameter. For example, a 95% confidence interval means that if we repeated the experiment many times, 95% of those intervals would include the true value. This concept is fundamental in statistics, as it helps us understand the reliability of our estimates and the likelihood that our results reflect reality. Significance level, often denoted as alpha, is the probability of incorrectly rejecting the null hypothesis when it is actually true, a type I error. A common significance level is 0.05, which corresponds to a 95% confidence level. This threshold helps us decide how much risk we're willing to accept for making a false positive decision. Choosing the right significance level is an important part of hypothesis testing. Confidence level and significance level serve different purposes in statistics. The confidence level focuses on the precision of an estimate, while the significance level focuses on the risk of error in hypothesis testing. Confidence levels are used to construct confidence intervals, giving us a range where the true value likely falls. Significance levels, on the other hand, help us decide whether to reject the null hypothesis. Understanding both is key to interpreting statistical results. P-value is the probability of observing a result as extreme as your data, assuming the null hypothesis is true. Think of the null hypothesis as the default or no effect assumption. For example, if you're testing a new drug, the p-value tells you how likely it is to see your results if the drug really has no effect. A small p-value suggests that your results are unlikely under the null hypothesis, casting doubt on its validity. Let's use a coin toss analogy to understand p-values. Suppose your friend claims they have a fair coin, the null hypothesis. You flip the coin 10 times and get 8 heads. The p-value is the probability of getting 8 or more heads in 10 flips, assuming the coin is truly fair. If this probability is very small, it suggests the coin might not be fair. This analogy helps make the concept of p-values more intuitive. Hypothesis testing, we compare the p-value to a predetermined significance level, usually 0.05. If the p-value is less than or equal to alpha, our results are considered statistically significant, and we have enough evidence to reject the null hypothesis. If the p-value is greater than alpha, the results are not statistically significant, and we fail to reject the null hypothesis. This comparison is at the heart of statistical decision-making. Statistical significance means that the observed results are unlikely to have occurred by random chance, given the null hypothesis is true. When the p-value is less than or equal to the significance level, we say the results are statistically significant. This doesn't guarantee practical importance, but it does suggest that the effect is real and not just a fluke. Always interpret statistical significance in the context of your research question. If the p-value is greater than the significance level, the results are not statistically significant. This means we fail to reject the null hypothesis, as the observed result could easily be due to random chance. It's important to note that non-significant results don't prove the null hypothesis is true, they simply indicate a lack of strong evidence against it. Always consider the context and the power of your test when interpreting these outcomes. Confusion matrix is a table that helps visualize and evaluate the performance of a machine learning model, especially for classification problems. In hypothesis testing, it summarizes the possible outcomes: true negatives, true positives, false positives, type I errors, and false negatives, type II errors. This matrix provides a clear way to understand the accuracy and error rates of your decisions, making it a valuable tool for both statistics and machine learning. Let's break down the 4 possible outcomes in a confusion matrix for hypothesis testing. True negative Tn, the null hypothesis is true and the test correctly fails to reject it. True positive Tp, the null hypothesis is false and the test correctly rejects it. False positive Fp, the null hypothesis is true but the test incorrectly rejects it, type I error. False negative Fn, the null hypothesis is false but the test incorrectly fails to reject it, type II error. Accuracy measures the overall correctness of a model or test. It's calculated as the sum of true positives and true negatives divided by the total number of cases. Error rate, on the other hand, tells us how often the classification was wrong, calculated as the sum of false positives and false negatives divided by the total. These metrics help us evaluate the performance and reliability of our statistical tests. Sensitivity, also known as the true positive rate, measures how often actual yes cases are correctly predicted as yes. Specificity, or the true negative rate, measures how often actual no cases are correctly predicted as no. These metrics are especially important in medical testing and other fields where the cost of errors can be high. High sensitivity and specificity indicate a reliable test. Precision measures how often the predicted yes is actually correct. It's calculated as the number of true positives divided by the total number of predicted positives. High precision means that when the model predicts a positive outcome, it's usually right. This metric is particularly useful when the cost of false positives is high, such as in spam detection or medical diagnoses. Sample size refers to the number of observations or participants included in a study. It's a crucial factor in statistical analysis, affecting the precision, reliability, and validity of research findings. Choosing the right sample size ensures that your results are both meaningful and trustworthy, providing a solid foundation for any statistical test or model. Importance of sample size can't be overstated. It affects the margin of error in estimates, determines the power of statistical tests, influences the confidence level of results, and impacts the ability to detect significant effects. A sample that's too small may lead to unreliable results, while an unnecessarily large sample can waste resources. Striking the right balance is key. In dealing with an infinite or very large population, the sample size can be calculated using a specific formula. N equals Z2 P1 P, E2, where Z is the Z-score for the confidence level, P is the estimated proportion 0.5 if unknown, and E is the margin of error. For example, with a 95% confidence level, 5% margin of error, and unknown proportion, the sample size would be about 385. Let's walk through an example. For a 95% confidence level, the Z-score is 1.96. If the margin of error is 0.05 and the estimated proportion is 0.5, the sample size formula gives us N equals 1. 96 2 times 0.5 times 1 0.5/0, 0.052, which equals approximately 384.14, rounded up to 385. This calculation ensures that our sample is large enough to provide reliable results. In working with a known finite population, we adjust the sample size using a correction factor. The formula is n-adjusted equals n1 plus n1/n, where n is the sample size for an infinite population and n is the total population size. This adjustment ensures that our sample size is appropriate for the actual population, avoiding unnecessary oversampling. For example, if the sample size for an infinite population is 385 and the population size is 1000, the adjusted sample size is calculated as n-adjusted equals 385/1 plus 385-1/1000, which comes out to about 371. This ensures that our sample is both efficient and statistically sound for the given population size. We've covered a lot of ground in this unit, from the basics of hypothesis testing to the details of p-values, errors, confidence levels, and sample size calculations. Each concept builds on the previous one, creating a comprehensive framework for statistical analysis. Mastering these ideas will help you tackle real-world data problems with confidence and precision. Understanding hypothesis testing and related concepts is essential for anyone working in data science, machine learning, or research. These tools allow you to make informed decisions, validate models, and draw meaningful conclusions from data. Whether you're designing experiments or analyzing results, these skills are invaluable in today's data-driven world. While hypothesis testing is powerful, it's important to watch out for common pitfalls. Misinterpreting p-values, ignoring the context of results, or choosing inappropriate significance levels can all lead to incorrect conclusions. Always ensure your analysis is grounded in sound statistical reasoning and consider the broader implications of your findings. Modern statistical analysis often relies on software tools to perform calculations and visualize results. Tools like Python, R, and specialized statistical packages can automate hypothesis tests, generate confidence intervals, and create confusion matrices. Familiarity with these tools enhances your efficiency and accuracy in data analysis. In using statistical software, it's crucial to understand the output. Look for key values like p-values, confidence intervals, and test statistics. Interpreting these correctly ensures that your conclusions are valid and actionable. Don't just rely on software, always apply your statistical knowledge to make sense of the results. Clear communication of statistical results is essential. Use simple language, visual aids, and concise summaries to convey your findings. Whether you're presenting to technical or non-technical audiences, clarity and transparency help ensure your insights are understood and actionable. Ethical considerations are vital in statistical analysis. Always report results honestly, avoid manipulating data to fit desired outcomes, and respect privacy and confidentiality. Ethical practices build trust and credibility in your work, ensuring that your analyses contribute positively to the field. Let's quickly review some key formulas. For sample size in infinite populations, use n equals z2p1p e2. For finite populations, adjust with n adjusted equals n1 plus n1/n. For accuracy, use tp plus tn/total, and for error rate, fp plus fn/total. Keeping these formulas handy will help you tackle a wide range of statistical problems. All these statistical concepts, hypothesis testing, p-values, confidence levels, errors, and sample size are interconnected. Understanding how they relate helps you design better experiments, interpret results more accurately, and make stronger data-driven decisions. Think of them as parts of a larger toolkit for tackling complex data challenges. Let's revisit our earlier example. A company claims its new drug has no effect on blood pressure. By setting up null and alternative hypotheses, collecting sample data, and performing a hypothesis test, we can objectively evaluate the claim. The process involves calculating p-values, considering errors, and interpreting the results in context. This structured approach is widely used in medical research and beyond. Hypothesis testing isn't just for traditional statistics, it's also fundamental in machine learning. Confusion matrices, accuracy, precision, and error rates are all used to evaluate model performance. Understanding these concepts helps you build, test, and improve machine learning models, making your work more robust and reliable. Statistics is a vast and evolving field. Staying updated with new methods, tools, and best practices is essential for success. Make it a habit to review foundational concepts, practice with real datasets, and seek out new learning opportunities. Continuous learning keeps your skills sharp and your analyses relevant. To deepen your understanding, explore textbooks, online courses, and research articles on statistics and hypothesis testing. Many universities and platforms offer free resources, and practicing with real-world datasets can solidify your knowledge. Don't hesitate to seek help from instructors or peers when you encounter challenging topics. Beyond formulas and calculations, developing statistical intuition is key. Try to relate concepts to everyday situations, question assumptions, and think critically about data. With practice, you'll start to recognize patterns and make informed decisions more naturally, both in your studies and in real-world applications. To wrap up, we've explored the essential elements of hypothesis testing: p-values, errors, confidence and significance levels, and sample size. These concepts form the backbone of statistical analysis in AIML and beyond. Remember, a solid understanding of these topics empowers you to make better decisions and contribute meaningfully to data-driven projects. Now that you have a strong foundation in hypothesis testing and related concepts, it's time to apply what you've learned. Work on practice problems, analyze real datasets, and experiment with statistical software. The more you practice, the more confident and skilled you'll become in applying these techniques to solve real-world problems. Welcome. Today we'll explore the receiver operating characteristic, or ROC curve, a fundamental tool in evaluating binary classification models. Whether you're new to data science or brushing up on your skills, understanding the ROC curve is essential for interpreting model performance. We'll break down what the ROC curve is, how it's constructed, and why it's so widely used in statistics and machine learning. By the end of this video, you'll have a clear grasp of ROC curves, AUC, t-tests, and ANOVA, and how they all fit together in the world of statistical analysis. Let's get started with the basics of the ROC curve. ROC curve is a graphical representation that illustrates the performance of a binary classification model across all possible thresholds. On this curve, the y-axis represents the true positive rate, also known as sensitivity or recall, while the x-axis shows the false positive rate, which is calculated as 1 minus specificity. By plotting these two metrics against each other, the ROC curve provides a comprehensive view of how well a model distinguishes between two classes. This visualization helps you see the trade-off between sensitivity and specificity as you adjust the decision threshold. True positive rate, or TPR, is a key metric in the ROC curve. It measures the proportion of actual positives that are correctly identified by the model. In other words, it tells us how good the model is at detecting positive cases. TPR is also called sensitivity or recall, and it's calculated by dividing the number of true positives by the total number of actual positives. A high TPR means the model is effective at catching positive instances, which is especially important in fields like medical diagnostics where missing a positive case can have serious consequences. The flip side, the false positive rate or FPR measures the proportion of actual negatives that are incorrectly classified as positives. It's calculated as 1 minus specificity, or the number of false positives divided by the total number of actual negatives. A low FPR means the model is good at avoiding false alarms. Balancing TPR and FPR is crucial, as improving one often comes at the expense of the other. The ROC curve helps visualize this balance, guiding you to select the optimal threshold for your specific application. Let's make this concrete with an example. Imagine you have a dataset of weight measurements to distinguish between obese and not obese individuals. The not obese group includes weights like 43, 44, 49, and 52 kilograms, while the obese group has 47, 55, 57, and 63 kilograms. Applying different thresholds, you can see how the model's predictions change, affecting both the true positive and false positive rate. This hands-on approach helps you understand how ROC curves are constructed from real data. Now let's visualize the ROC curve using our sample data. As you adjust the classification threshold, you plot the corresponding TPR and FPR values on the graph. Each point represents a different threshold, and connecting these points forms the ROC curve. The closer the curve hugs the top left corner, the better the model's performance. This visual tool makes it easy to compare different models or thresholds at a glance. Looking at the ROC graph, you can immediately see how well your model separates the two classes. A curve that rises quickly towards the top left corner indicates high sensitivity and low false positive rate. If the curve is close to the diagonal, it means the model isn't much better than random guessing. This visual feedback is invaluable for model selection and tuning, helping you make data-driven decisions. Area under the curve, or AUC, is a single number that summarizes the entire ROC curve. It tells you how well the model can distinguish between the two classes. In simple terms, the higher the AUC, the better the model is at ranking a random positive instance higher than a random negative one. AUC is widely used because it provides a clear, quantitative measure of model performance. AUC values range from 0.5 to 1. An AUC of 0.5 means the model has no discriminatory power, it's no better than flipping a coin. An AUC of 1 represents perfect classification, where the model always ranks positives higher than negatives. In practice, AUC values between 0.7 and 0.8 are considered acceptable, 0.8 to 0.9 are excellent, and above 0.9 are outstanding. This scale helps you quickly assess and compare different models. Real-world applications, AUC is a go-to metric for evaluating classification models, especially when dealing with imbalanced datasets. It's robust to changes in class distribution and provides a holistic view of model performance across all thresholds. Whether you're working in healthcare, finance, or marketing, AUC helps you choose the best model for your needs. Now that we've covered ROC curves and AUC, let's shift gears to another foundational concept in statistics, the distribution of the sample mean. This idea is crucial for understanding how sample averages behave and why statistical tests like the t-test work. We'll use a simple analogy to make this concept easy to grasp. Imagine a big jar of candy representing your population. Some candies are big, some are small, and a few are giant. The average size of all candies in the jar is the population mean. Since you can't measure every candy, you take a handful, say 50 candies, find their average size, and write it down. You repeat this process each time, recording the average. The collection of these averages forms the sampling distribution of the sample mean. Sampling distribution of the sample mean shows how the means of different samples, all of the same size, would vary if you took them from the same large population. This distribution helps you understand the variability of sample means and how they cluster around the true population mean. It's a key concept for making inferences about populations from samples. Central limit theorem is a cornerstone of statistics. It states that if you take an infinite number of samples from a population and plot each sample's mean, those means will form a normal-like distribution regardless of the population's original shape. This theoretical distribution is centered around the true population mean, and its standard deviation, called the standard error, measures how much the sample means typically vary. Standard error is the standard deviation of the sampling distribution of the sample mean. It tells you how much the sample means are expected to vary from the true population mean. A smaller standard error means your sample means are tightly clustered, while a larger standard error indicates more variability. This concept is fundamental for constructing confidence intervals and conducting hypothesis tests. Both the z-test and t-test use the concept of sampling distribution to answer the question, how unusual is my sample mean, assuming the true population mean is a certain value. The main difference is that the z-test is used when the population standard deviation is known and the sample size is large, while the t-test is used when the population standard deviation is unknown or the sample size is small. T-test is a statistical tool used to determine if the means of two groups are significantly different from each other. In other words, it helps you figure out if the observed difference between two averages is likely due to random chance or if it's a real, statistically significant difference. T-tests are widely used in research, business, and healthcare to compare groups and draw meaningful conclusions. You should use a t-test when you're comparing the means of two groups. Your data are numerical, and the data are approximately normally distributed. It's especially useful when the population standard deviation is unknown or your sample size is small, typically less than 30. If you have 3 or more groups, you'll need to use an ANOVA test instead. There are 3 main types of t-tests: the one-sample t-test, the independent samples t-test, and the paired samples t-test. Each type is designed for a specific scenario depending on the structure of your data and the question you're trying to answer. Let's break down each type and see when to use them. One-sample t-test compares the mean of a single group to a known value or a theoretical population mean. For example, you might want to know if the average height of students in your class is different from the national average. The formula involves the sample mean, the hypothesized population mean, the sample standard deviation, and the sample size. Formula for the one-sample t-test is t equals mu s/square root n, where x is the sample mean, mu is the known or hypothesized population mean, s is the sample standard deviation, and n is the sample size. This formula helps you determine if the observed difference is statistically significant. Independent samples t-test, also known as the two-sample t-test, compares the means of 2 unrelated or independent groups. For instance, you might compare the test scores of students who used a new study method versus those who used the old method. This test helps you determine if the difference between the two group means is statistically significant. Formula for the independent samples t-test is t equals x1 x2/sqrt, s12/n1 plus s22/n2, where x1 and x2 are the sample means, s1 and s2 are the sample standard deviations, and n1 and n2 are the sample sizes for each group. This formula assumes equal variances and helps you assess if the observed difference is meaningful. Paired samples t-test, also called a dependent t-test, compares the means from the same group at 2 different points in time or under 2 different conditions. For example, you might measure a person's blood pressure before and after taking a new medication. This test is ideal when your data points are paired or related in some way. Formula for the paired samples t-test is t equals est/square root n, where it is the mean of the differences between paired observations, est is the standard deviation of those differences, and n is the number of pairs. This test helps you determine if the change between conditions is statistically significant. Let's look at some visual examples of comparing two groups. These graphs help you see how the means and distributions of each group differ, making it easier to interpret the results of your t-tests. Visualization is a powerful tool for communicating statistical findings. Here's another example of comparing two groups using visual data. By plotting the distributions side by side, you can quickly spot differences in means, spread, and overall shape. This approach helps you understand whether the observed differences are likely to be statistically significant. Visualizations are not limited to just two groups. Here, you can see how data from multiple groups can be compared using charts and graphs. These visuals make it easier to identify patterns, trends, and outliers, setting the stage for more advanced statistical tests like ANOVA. When comparing more than two groups, visual tools become even more important. By displaying the data for each group, you can see how their means and distributions differ. This visual approach helps you decide whether a more advanced test like ANOVA is needed to analyze the differences. As you move to more complex analyses, comparing multiple groups requires careful statistical methods. Visualizations like box plots and bar charts help summarize the key differences and guide your choice of statistical tests. These tools are essential for clear and effective communication of your findings. You need to compare the means of 3 or more groups. ANOVA, short for analysis of variance, is the tool of choice. ANOVA is a powerful statistical technique that examines the variance within and between groups to determine if the group means are significantly different from each other. Let's break down how ANOVA works and why it's so useful. ANOVA stands for analysis of variance. Instead of directly comparing the means, ANOVA examines the variance within the data. It splits the total variability in 2 parts: between group variance, which measures how much the group means differ from the overall mean, and within group variance, which captures the natural variability within each group. This approach helps you determine if the observed differences are real or just due to random chance. Between-group variance measures how much the means of each group differ from the overall mean. If the between-group variance is large compared to the within-group variance, it suggests that the group means are truly different. This is the key logic behind ANOVA. Large between-group variance points to real differences, not just random fluctuations. Within-group variance captures the natural variability of data points within each individual group. Even if the group means are the same, there can be a lot of spread within each group. ANOVA compares this within-group variance to the between-group variance to decide if the group means are significantly different. Core logic of ANOVA is simple. If the variation between groups is much larger than the variation within groups, it suggests that the differences in group means are real and not just due to random chance. This statistical approach allows you to test multiple groups at once, making it a powerful tool for research and analysis. Use ANOVA when you have 3 or more groups and want to know if their means are significantly different. It's commonly used in experiments, surveys, and business analysis where multiple groups or treatments are compared. ANOVA saves you from running multiple t-tests, reducing the risk of false positives. In practice, ANOVA is used in a wide range of fields, from agriculture to medicine to marketing. For example, a company might use ANOVA to compare the effectiveness of 3 different advertising campaigns. By analyzing the variance, they can determine if one campaign truly outperforms the others. Visual representations, such as box plots or bar charts, are often used to display ANOVA results. These visuals make it easy to see differences between group means and understand the spread of data within each group. Effective visualization is key to communicating your findings clearly. Let's recap what we've covered so far. We explored the ROC curve and AUC as tools for evaluating binary classification models, learned about the sampling distribution of the sample mean, and delved into t-tests and ANOVA for comparing group means. Each concept builds on the last, giving you a solid foundation in statistical analysis. Choosing the right statistical test depends on your data and research question. Use ROC and AUC for classification models, t-tests for comparing 2 groups, and ANOVA for 3 or more groups. Understanding these tools helps you draw accurate and meaningful conclusions from your data. Be aware of common pitfalls, such as using the wrong test for your data or misinterpreting results. Always check your data's assumptions like normality and independence before applying statistical tests. Careful analysis ensures your conclusions are valid and reliable. Statistical tests like ROC, AUC, t-tests, and ANOVA are used in countless real-world scenarios. From evaluating medical treatments to analyzing marketing campaigns, these tools help professionals make data-driven decisions. Mastering them opens doors to deeper insights and better outcomes. To get the most out of your statistical analysis, always start with a clear research question, choose the appropriate test, and visualize your results. Double-check your calculations and interpret findings in context. These best practices will help you communicate your results with confidence. If you want to dive deeper, there are plenty of resources available, from textbooks and online courses to tutorials and forums. Continuous learning is key to mastering statistics and staying up to date with the latest techniques and tools. Congratulations, you've now gained a solid understanding of ROC curves, AUC, sampling distributions, t-tests, and ANOVA. These concepts are foundational for anyone working with data. Keep practicing, explore real datasets, and continue building your statistical toolkit. The more you apply these concepts, the more confident and skilled you'll become in data analysis. Thank you for joining us on this journey through Unit 3 of Computational Statistics. We hope you now feel more confident in your understanding of hypothesis testing, p-values, and related concepts. Keep exploring, keep questioning, and remember, statistical thinking is a powerful tool in your AIML toolkit. See you in the next video.